I'll talk about mutual information and graph neural networks. So this is related to the some of the topics we had in the tutorials on Monday, where we had some talks about graph neural networks, and we also had a tutorial about the information bottleneck method. So also a part of the information bottleneck method is also to look at the gradients during training, but I didn't do that. So here it's most of the mutual information and the information plane I'm focusing on. So a question I had going into this was if we could investigate the inductive bias of different graph neural network architectures. And the inductive bias is basically when you design a new algorithm, you are trying to leverage the structure in the data in a certain way. And here we can see basically maybe an increasing order of complexity to how you do that. And MLP has no particular inductive bias related to the graph structure of the data. So here Zi-1 is the previous layer's representations. You matrix multiply this and apply nonlinearity, and you get your new representation. While in the graph convolutional network, instead of simply using the previous representation here for node n, you perform a pooling operation along its neighbors in the graph. So here in the GCN model, for each step or each layer, you're using your knowledge of the adjacency matrix in order to compute the next representation. And in the GCN, this is a fixed factor, a fixed weighting of your neighbors, and the weighting is based on these d hats, which come from the degree of the node, how many edges are to it. So a node with more edges would have way higher. In the graph attention mechanism, there's also a similar, this alpha, it's like as an attention to the node's neighbors and also to the edges. So whilst in the graph convolutional case, this was fixed based on what was in the edge matrix, now this can be used as learnable parameter to the model in addition to WI. So so a bit the scope here is that we will look at the graph convolutional architectures and compare how we do in the classification as far as validation and training accuracy, and also visualize the information plane. So if we could learn something more about how they are learning the task through the information plane. And the information plane, this is here you can see the shading. The light is at the start of training, and then it gets darker and darker as you get further out along in the training. So what could this tell us? Well, first of all, you have the data here, and we're only looking at classification tasks right now. So Y are kind of labels for the categories you want. And this step, we think it's nature that creates the features for the data. For example, if this is like the iris data set and these are flowers, and it's nature that generates these attributes. And then we're trying to reverse this. And what we're trying to capture in the information plane is what kind of information are we leaving out, and what kind of information are we trying to pertain. So L5, it would represent the final layer. And from this information plane, what we could extract is that the final layer, it's able to retain little information about the input data X, but during training, it gains more information about the output data Y. So what this tells us is that this final representation is able to generalize away many unnecessary sources of variation in X, and only retain parts of X that are relevant for predicting Y. So we consider that a desirable attribute of the features that are able to like retain parts that are relevant for predicting Y. And a part of this information plane analysis relies also on the data processing inequality. So here, if we have matrices between these layers, you cannot gain information about X or Y by applying a function that doesn't otherwise contain information about X and Y. So at least for a multilayer perceptron, we would expect this to be, well, it must be satisfied. And then for the graph convolutional and graph attention networks, this is not necessarily the case because you're augmenting the features of each node by its neighbors, right? So at each step, you're using information in the data to produce a new representation. So the data processing inequality doesn't have to be satisfied. So the main challenge really in creating these is estimating the mutual information, and I've used a method from this Kolchinsky and Tracy paper, estimating mixture entropy with pairwise distances. And here, so basically here P of T is the hidden representation, and we have to assume it is as a normal distribution with some noise because it's deterministic, right? But if we assume it is a normal distribution, we're able to attain bounds based on the pairwise distances between. So for one hidden representation, this is the pairwise distance matrix between the elements of the data set in that representation. And this could become expensive also as you have more data. So yeah, so here we also see the part where it's specified for a classification target. It's because if you only have h of t given y, you can condition it on the class label, but this would be a bit more complicated, for example, in a regression setting. And so that's why we're focusing on the classification task. So we're looking at the node property prediction, and then we're also looking at the archive data set. So the archive data set, it's you have a graph where each node is an article, and the feature vector is obtained by running a skipgram model, and you get feature this way. And there are 40 subject classes to predict these papers into. Zinc and QM9 datasets are not really suitable for creating these information planes because here you're putting in like entire graphs and molecules, but really the setup for this, at least this mutual information plane and the estimator is more of node prediction, where you have a standard data set with a shape of n, d. That's kind of what we're looking after for. So here I'll show the information planes for the graph convolutional network and the graph attention network. And so first of all, we could note that the data processing inequality, at least for the graph convolutional network, is not satisfied. This is not a big deal, but what we could see here is that the final layer is the square, and then the triangle is the second layer, and the circle is the first layer. So here we see that by having the fixed pooling operation on the edge, based on the edge adjacency matrix, the feature representation are gaining information about X because they're learning about their neighbors and their features. So there we see that the network is learning more and more information about X, but it's not really learning more about Y. While in the graph attention case, here we see that the first and second layer were pretty coupled, and that the last final third layer here actually doesn't retain as much information about X as those earlier layers. So we could maybe think that by having the attention weights being learnable, that it says like we don't need all this information in X. And we could also note that it's yeah. No. Yeah, so these are the validation and training planes. So we see that even though the graph attention network has a bit less information in X than the GCN, it still doesn't really display that in the validation plane. So, well, one could have comments to these that, well, you should add regularization and we should add more parameters, and I agree that could be done. But the point here was to say that we wanted to analyze a model from an accuracy point of view and also from the information plane point of view to see if they're just to find some relations. And then the framework here, really, you could define your model like this, and then you would attach a PyTorch on these, and you would track the activation as it goes through the network. And then depending on how much data you have, you should either compute it, you kind of need the whole representation for that epoch to compute the mutual information plane. And so there are some computational issues related to storing the activations or computing the information values right away, and also computing the pairwise distances. So that's it. You could check out the code, or and there's my contact email.